Okay.
Today we will discuss about generator ventilation system as per manufacturer. Okay, we will see how to calculate the generator ventilation fan capacity and what is the purpose of generator ventilation, why it is required. Okay, see, this is one of the layout. Okay, where you can see the building services. There is one floor. Okay, you can see the layout. Right, there is a transformer room. Then you can see there is a generator room. Right. Then after that you can see there will be LV room. Okay, you can see there is a LV room here. Right. Okay, now basically, okay, there will be a power from authority, right? Maybe the local authority will give you the power to the our buildings, right? Okay, when the power comes from authority through the transmission line, it will come to the HV room, okay, or you can say high voltage room, right? Then through the high voltage room, it will come to our LV panel. Okay, so through the LV panel, you cannot directly come into the LV panel because high voltage to the low voltage, there will be some equipment is required between the to step down the voltage, right? So that is why you have a transformer. Okay, so during the normal scenario, your power will come from authority to the through the transmission line. It will come to the HV room, then it will reach to the LV room through the transformer room. You clear? Okay.
Yes.
Okay. Now, say for example, there is a power failure scenario. So what will happen? The transformer will will not get a power, right? Because the HV, the power from authority will not receive any signal. Okay. Then that means the power will not be transferred through the transformer to the LV room. So it's not possible, right? So what will happen? That time you have a backup that is called generator, right? So it will give you the backup power supply. Okay. So when you talk about backup power supply, the transformer will have a two type of generator. Okay. So generator, you can say high voltage generator and also you have a low voltage generator. Okay. So when you design with a low voltage generator, the generator can give you directly the power to the LV room. If you go with the high voltage generator, then the generator will give you the power LV room through the transformer room. Clear, right? So this is the procedure. So the power
Yeah.
comes from authority. One is authority power, another one is a backup power, which is comes from generator. Okay, the authority power comes from authority to the transmission line. Then it will reach to the HV room. Then from the HV room, it will go to the LV room through the transformer room because it has to step down from high voltage to the low voltage. Okay, and in case of power failure, the power will not come from HV room, right? The power will come from generator. Okay, so when the power is shut off, then the generator will start immediately. It will get start through the ATS. There will be automatic transfer switch. So the transformer switch will give the signal to the generator to switch on, saying that there is a power failure. There is no power from authority line. Okay, so now this is the generator, correct? So when the generator runs, what will happen? You can see there is a section, right? You can talk about there is a generator here. Okay, so the generator will give you power to the buildings. Okay, so when the generator runs, what will happen? It will dissipate a heat. Any equipment dissipate a heat, right? Whether it's a transformer or generator or any of the computer rooms or whatever the computer appliances or any kitchen appliances, it will dissipate a heat. Okay, so even the generator also will dissipate a heat, right? So that heat to be taken out from the generator room. Otherwise, generator will get overheated up and maybe it will shut down. Generator, maybe there is a chance of shutdown or there is a chance of fire because of the high temperature. Okay, it may burn. Okay, or it will trip. Okay, so either one will happen, right? Clear, right? So due to the high heat dissipation, okay, what will happen? Your generator will have a less efficiency. So we have to design a fan, okay, to take out all the heat from the whatever the heat generated from the heat generator should be taken out from the generator room. Okay, so that is why we are going to calculate. Okay, now that is one of the parameter. Okay, you are going to take out all the heat from the generator room to be taken out from the generator room. So that is one of the parameter. Second one, when the generator runs, right, you need a combustion, right? The generator is a generator consists of fuel. The fuel has to burn, right? And you know the fire triangle. So the fuel, right? Then the heat and also the fuel. Three things required for the generator to burn. Okay, so the oxygen is required, right? One is oxygen, another one is heat, another one is a fuel. Three things are required. Okay, so where the oxygen comes from? That oxygen should come from outside. So you have to supply the oxygen as well. So whenever you ventilate the generator room, one for the cooling the generator, another one for the combustion purpose. So that is the way you have to calculate your generator fan capacity. So if you go to one of the guideline, so this is the guideline, engine room ventilation, okay, sizing consideration. One is for cooling air and another one is for combustion air. Okay, so you require cooling air for cool the generator. Okay, another one is combustion air for the combustion, right? So this is the way sizing consideration. So if you go further down, so this is for cooling air. A portion of the fuel consumed by an engine is lost to the environmental in the form of heat radiated to the surrounding air. In addition, heat from the generator, inefficiencies and exhaust piping can easily equal engine radiated heat. Okay, so from the engine there are a lot of inefficiency heats. So that to be taken out. Okay, clear, right? And also there is a combustion of air. You require air for the combustion purpose. Okay, so you can say calculating required ventilation. So this is a simple equation, Q equal to mCp delta T, right? We know the heat transfer equation. So this is the same equation here. V equal to ventilating air, H is nothing but heat radiation, D is nothing but density of air, and Cp is nothing but specific heat of air, and delta T is the permissible rise in engine generator. Okay, so what is the permissible temperature rise from the generator? Okay, that we have to see. Clear, right? So that is the way you will get delta T. Okay, so this one where you will get delta T. If you go to one of the chapter, okay, let me open the guideline. You can see the temperature. What is the temperature difference, right? So you can go to diesel generator, right? This is a diesel generator, and what is the minimum temperature difference? Okay, so here the temperature difference is given here, right? The design outdoor plus 6 degree, that will be the ambient temperature. Maximum temperature will be design indoor plus 6 degree. Clear, right? So the generator can work plus 6 degree from the ambient temperature maximum. Okay, otherwise it will get tripped. Okay, this is as per ASHRAE guideline. Okay, so when you calculate your temperature, what is the maximum temperature, ambient temperature? Say for example, in UAE we have a 46 degree Celsius. So plus 6 degree will be, say for example, 46 plus 6, it can work up to 52 degree Celsius. The generator, after more than 52, it may get tripped or it will be overheated. So you have to maintain the temperature with less than 6 degree delta T. Clear, right? Okay, so that is the way you have to calculate your ventilation requirement. So V is nothing but ventilating air, H is nothing but heat radiation, this from the heat from the generator, and D is nothing but density of the air, Cp is nothing but specific heat, and delta T is nothing but permissible temperature rise in engine room, right? You can see that maximum engine room temperature is 120 degree Fahrenheit. Okay, this is depends upon normal standard. Okay, but as per ASHRAE guideline, you can say design ambient plus 7 degrees, 6 degrees Celsius. Or maximum, it can go 7 degree temperature. Okay, based on that only you will calculate. Okay, but if you go to manufacturer, they will give you directly what is the airflow required for the cooling purpose. Say for example, you have a cooling system. What is that maximum temperature? What is the maximum airflow rate is required? 14.5 meter cube per second. Okay, so this is the required airflow rate for cool the radiator. Okay, if you go to generator, this is your generator, right? This is your generator. Okay, so here you will be having a say for example, alternator will be there. Okay, you have to cool the alternator, right? Sorry, basically radiator. Okay, you have to cool the radiator. Okay, so for the radiator, for cooling the radiator, you require air from outside. So that particular air will be given in the directly in the catalog. So which is 14.5 meter cube per second. Also, they have given the total heat rejection, which is BTU per minute, 21,610. Okay, so this is the heat which comes from the generator as a peak temperature. Okay, but you can also calculate the airflow rate or the heat dissipation which comes from this using this equation. Using this equation, you can also calculate your ventilation here. Heat is nothing but heat radiation BTU per minute, right? So that same value is given here. BTU per minute. This is the heat from the generator. Okay. Then D is the density of the air, which is given here, 1.09 kg per meter cube. Cp is nothing but specific heat of air, which is 0.017 kilowatt, right? Kilowatt multiplied by minute by kg into Celsius. So this is specific heat. Okay, then the delta T will be permissible heat rise. So in this way also you can calculate ventilation airflow rate, or you can go to the manufacturer catalog. They will give you directly 14.5 meter cube per second or 14,500 liter per second. Okay, so this is the required for radiator cooling. And what about for the combustion? So this is the air required for combustion purpose, 52.7 meter cube per minute. If you multiply by 60, it will give you 52.7 multiplied by 60 meter cube per hour, or divide by 60, it will give you meter cube per second. So when you add together, it will give you total ventilation airflow required. So if you go to one of the guideline or one of my previous project, okay, you can see the calculation for the exhaust air and for the radiator intake. So what is the calculation method? You have a generator capacity, dimension, then what is the engine airflow rate from the catalog, radiator airflow rate from the catalog. So this engine airflow rate 2.3 meter cube per second is nothing but this value for combustion air. 52.7 divided by 2.60 will give you what is the combustion air. So that value should be here, should be given here. Then radiator airflow rate, which is 30.2 is given here for different model, 2000 kVA model, but we are referring different model. Okay, so that one value is given here, 14.5 meter cube per second. Okay, so when you add together, it will give you the total intake airflow rate, engine airflow plus radiator airflow. So this is the 32.5 meter cube per second. This is the intake airflow rate. So it's nothing but ventilation airflow rate, the fan capacity. Okay, now what is that exhaust? You can talk about 30.2, which is the radiator airflow. So whatever the air comes from outside, okay, the engine, whatever the air required for engine, it will burn and it will supply through the pipe as a flue gas. Okay, only the radiator airflow will be cooled the radiator and it will be discharged outside. So this is the exhaust airflow rate. It's clear, right? Anyone have doubt? How to calculate ventilation airflow rate for generator?
Awesome.
Clear, right?
Okay.
Okay. So now if you go to the guideline, okay, if you go to guideline, this is your generator room. Okay, assume that this is my generator room. This is my generator room, right? So what is my arrangement? This is my intake and this is my discharge, right? So it is inline. You can say inline. So if it is inline, if you go to the guideline, okay, this is like inline, right? So this is the intake and this is the discharging out and it is going. So this is a factor, one factor. Okay, so one factor means whatever you calculate the flow rate, multiply by 1 times, because it is inline. Okay, if you go ventilation type 2, okay, again that is inline, right? If you go to ventilation type 3, it is not inline, right? It is not in front of the radiator. It is somewhere away from the radiator. So then you have to multiply by 1.5. So whatever the calculation you calculate, you have to multiply by 1.5 because you require more air to cool the radiator because it is not inline, right? So if you design your generator room such a way that if it is inline, then you don't need to go with the multiply by 1.5. You don't need to oversize the fan. Okay, but depends upon some architectural arrangement. If in case you cannot provide in front of the radiator, if you have to keep away from the radiator, then you have to multiply by 1.5 times to calculate your ventilation fan capacity. Okay, and you can see the another type. If you give supply on the top of the generator, then you have to multiply by 2.5 times because the radiator is here, but you're supplying on top of the generator, which it require more times to cool, right? Because there is a short cycle here. Okay, so the radiator will not get enough cooling. So that is why you are going to pump 2.5 times. Okay, and if you provide on the top of each other, this is the intake and this is the exhaust. If you provide like this, what will happen? The engine will get overheated. So this is incorrect airflow. So this method is not recommended. So that is why if you see any of the project, we have designed generator room in line with the transformer, so that the whatever the air comes from outside, it will go through the intake and it will cool the radiator, then it will be discharged outside as a hot air. Okay, and whatever the combustion air, it will come here, it will combust the fuel, then after that it will go as a fuel, as a flue gas, it will be taken out. Okay, so airflow is required for cooling the radiator, airflow is required for combustion purpose. So what is the cooling, what is the airflow required for cooling? It is given here. Cooling system airflow rate, which is 14.5 meter cube per second. That is what it is given here as well. Intake air sizing. What is the intake air sizing? Engine airflow rate plus radiator airflow rate. So what is the engine airflow rate? Which is given here in the catalog. And what is the radiator airflow? For cooling purpose, cooling the radiator. That is also given in the catalog. So when you add together, that will be the intake fan sizing. Okay, and for the exhaust, you have only radiator cooling, right? Whatever the radiator cool the radiator, that particular air will be hot air that will be discharged outside, because for the combustion air, it will be go through as a pipe as a flue gas, because it will convert from oxygen to flue gas. Clear, right? So this is the way to calculate ventilation fan capacity for intake and exhaust. Okay. If you go to this drawing again, okay, there are different scenario. Okay, assume that this is the enclosed room, right? Okay, assume that you're keeping the generator outside. There is no enclosed room. So then what will happen? It can draw the air from outside and it can cool the radiator, and also it will get the air from combustion. It will discharge outside, right? So there is no enclosure here. Assume that you're going with enclosure. You're going to keep it inside the generator room. What will happen? This particular generator has to take the air from outside and it has to discharge inside. Okay, when you have an enclosed room, you have a louver, you have an intake louver and you have a discharge louver, right? So when you calculate the pressure drop for the intake louver and for the exhaust louver, say for example I have a 12.5 Pascal, I have a 12.5 Pascal, then I will be having a duct connection. Assume that this is my duct mouth and I have a duct connection here, right? So assume that this is a 10 Pascal, okay? So 12.5, 12.5, 25 plus 10, it will be 35 Pascal, right? So when I have a generator, I have an inbuilt generator fan. So that is what, if you go to the catalog, there is an inbuilt fan which can deliver 14.5 meter cube per second at the rate of 12.7 mm H2O, which is nothing but 127 Pascal, right? So there is an inbuilt fan can work for 14,500 liter per second at the rate of 127 Pascal. Okay, so whenever I design my accessories, I should not go beyond 127 Pascal. Clear, right? So say for example 35 Pascal, my inbuilt fan will work. It can draw the air from outside and it can discharge it to the outside. Okay. Now I have another case. Say for example in nearest residential apartment. Okay. Then I should have a noise limitation. Okay. Then what I have to do? I may have to add the sound attenuator, right, for the intake and discharge to control the noise. Okay. So what will be the discharge? What will be the sound attenuator pressure drop? Assume 50 Pascal. Then intake will be 50 Pascal, right? So it will be 100 Pascal. Then I have an intake louver, discharge louver, then I have a duct connection which will come 150 Pascal. But what is allowed? I can go with only 127 Pascal. If it goes beyond that, then I have to go with the external fan. So what is the fan capacity? The same, engine radiator cooling plus engine air for the combustion. So the both will be the fan capacity for the intake. Is that clear? How to calculate generator fan ventilation capacity?